Greetings, folks. Here we go again. Same shirt, same hat, and same books behind me. Today we're going to talk about the direction of centripetal acceleration. Sometimes it's easy to find, sometimes it's not. But if you get it wrong, you're dead. So stay with me.
I know. People say I've changed. But aside from the beauty scrub that I've been using, I'm the same lovable guy I've always been. In any case, centripetal force problems. If you don't get the axis right, you're screwed. This video is hopefully going to help you not to mess that up. So here's our first situation. Ceiling rope is attached to a bob. The bob is motivated to follow the circular path like so. So what you're about to see here is a little animation so you can actually see the guy do the deed. So what we're going to do is we're going to do a little snapshot of the situation. So the string's coming down, the bob is here. Bob is coming out at us, and we're going to do a free body diagram for the bob as it sits in this position. So if we wanted to analyze this situation, we'd start with a free body diagram. We'd have tension coming up like so. We'd have gravity coming down like so. Here are our forces. And now as far as the approach goes, the Newton's second law approach, we want to identify the line of the acceleration. And the acceleration that's important here is the centripetal acceleration. It's the acceleration that's pulling or pushing the body out of straight line motion. And to do that, what we have to identify is the center of the arc upon which the body is moving. So here is the motion of the body, and the center of the arc is right there. So we're going to put an axis that's going to go from the body through the center of the arc, which is to say an axis like so. So here's our center seeking axis. Once you'd have your axes down, you'd follow the Newton's second law approach, which is to say you'd look for off-axis forces. In this particular case, tension is an off-axis force. You take the off-axis forces and you break them into their component parts along the axes. So you'd have these two tension components. You could sum up the forces along this line and put the sum of the forces equal to MA. A along this line is 0. The body is not accelerating along this line. And so you could relate T cosine theta to mg in that way. And then you'd sum up the forces in this direction, in the centripetal direction. And so you'd have T sine theta here, and that would equal the mass times the acceleration in this direction, which you've come to know as the magnitude of the velocity squared divided by r. The main point here, though, is that if you somehow or other got this coordinate axis wrong, you would end up trying to break the off-axis forces up in an inappropriate way, and you'd be dead from there on out. As soon as you got the axes wrong, everything from there on out would go south. And so it's important that you keep your head when you're trying to figure out what the centripetal direction is. So here we have a new situation. In this case, we have a ceiling again, a rope coming down to a bob, except in this case the bob is swinging back and forth like so, the way a pendulum would. And I've done a little animation for this also. Okay, so I'm going to do a stop action here, and I realize that in the video this is sort of where it started and it went back and forth. I'm going to assume that in fact it actually went further, so it's going to be more this kind of motion, which means I'm assuming that the body is actually moving when it's in this position right here, and that way there will be some centripetal acceleration going on. So as usual in a Newton's second law problem, we want to identify the forces. And so we've got tension going up in this direction, we've got gravity going down like so, which means our forces are exactly like the forces we had in the previous problem. There are two things that are different about this relative to the previous problem, though. The first is that the center of the arc that the body is moving on is here, which means we need to have a coordinate axis that goes, once again, from the body through the center of the arc, or an axis along that line. That means that there has to be a net force along that line, because apparently there is a centripetal acceleration along that line. Additionally, if this object is moving in this direction, we know it's slowing down. And if it's moving in this direction, we know it's speeding up. Which means once we have this axis, when we put the second axis in perpendicular, we're going to find that there is some net force along this line also, because there apparently is an acceleration along this line. So we're going to find an acceleration both in the centripetal direction, also in the tangential direction, which makes this problem quite different. In any case, once we go ahead and we get our axes set up, we have an off-axis force, which we would have to break out into its component parts, and then we would simply proceed on the problem as normal. This would be the axis whose MA term, the A term, would be V squared over R. This would be an axis whose MA term, A, would just be A. It would just be whatever the acceleration was that was changing the magnitude of the velocity vector. But again, what we're doing is we're looking at what's happening in this snapshot. So we're not wondering what's going to happen as it proceeds down or up. We're just looking at what's happening in the snapshot. So you can figure out what V is at this instant and what A is tangentially at this instant. And here you have the whole enchilada laid out. Here are the centripetal forces. They'll add, obviously this one's positive, this one's negative. The net force is going to equal MA, which is mv squared over r. This component is going to be the component that's going to accelerate the body. It's either going to slow it down if it's moving this way or speed it up if it's moving in this direction. And so that's this situation. That's this example. The last situation we're going to look at is this loop. And once again, I have an animation. So we're going to take a look at this snapshot. The body's come down to here, and it's right here at this point, proceeding upward. What are the forces acting on the body? You've got a normal force pushing in this direction. You've got gravity pulling down. So here are your forces. There's the normal, there's gravity. What is the center-seeking direction? What is the centripetal direction for your axis? Well, here is the arc that the body's moving on. Here is the center of the arc. We're going to go from the body through the center of the arc. Apparently we need an axis along this line, and we need an axis perpendicular to that line. And there we have our axes. New orientation, new situation. The body's come down, it's come all the way through the loop, and is now right here at this point. How would we analyze that situation? Again, we've got a normal force pushing out, and we've got gravity down. And so the question is, what is the line of the acceleration? What's the center-seeking direction? And again, this is the motion is along this line. That's the arc. The center of the arc is right there. The center-seeking direction, the line of the acceleration is from the body through the center of the arc. So we need an axis that's going to go like so, and an axis that's going to be perpendicular to it. Here are our axes. mg is an off-axis force, so you'd have to break it into its component parts, and you'd end up with a normal force coupled with a component of gravity combining to give you your centripetal force, net force. That would equal m times a sub c, which is mv squared over r. This component of gravity, the one along here, is the one that would be motivating the body to pick up speed as it was moving down through the arc. And here is sort of a summation of all of what I just said. So bottom line, to identify the line of the centripetal acceleration, you want to identify the center of the arc upon which the body is moving, and you want to draw an axis that goes from the body through that center. That's all there is to it. So I'm going to go have a facial. Have a nice evening.